Okay, so first up we have Bobby Filar, and he's a data scientist at Endgame. He won't tell anybody, but he's hiding because he just got promoted to director. Sorry. I know you didn't want anyone to know.
I told you that in confidence.
Sorry, there's no privacy here. So we met, we were on a panel on ethical attacking of and with machine learning, and I was pleasantly surprised to see we agreed on things. So he's talking today on attacking trees to understand them. Thank you.
All right, good. So yes, my name is Bobby, data scientist at Endgame. I'm really here to talk about how awesome this TreeHuggr logo is, more than anything else. But no, TreeHuggr is a framework that I've been kind of working on for the past 2 months with the sole purpose of discovering where within tree-based models we're prone to false positive, evasions, and potentially attacks. So a quick outline, I'm going to go over my motivation for working on this, a little bit of background use case about how we would potentially employ this at Endgame, dive into the framework itself with a hopefully intuitive explanation of the core algorithm I use to generate adversarial, in quotes, examples, hit a few use cases that I tried, experiments and whatnot that were met with varying degrees of success, and then finally challenges, next steps. So first, who in the audience has actually worked on adversarial ML at all? Hiram, thank you. All right, so more than I expected. One of the things I like the most about adversarial machine learning, particularly coming from InfoSec, is it's the closest thing we have to vulnerability research and kind of exploit development. And that's really cool because other than getting awesome presentations accepted at Black Hat and DEF CON, you can learn a lot about applications and in our case, models, features, and training samples within your data. The one problem that I have with it and kind of bums me out is that it's almost entirely based on neural networks. When folks in here probably work with tree-based classifiers more than anything else. So I wanted to do something to help with that, to go into model susceptibility, hopefully translate that into some sort of interpretability metrics and take it from there. So the problem that I kind of set out to solve was we have a malware classifier at Endgame called malware score. Phil Roth is around here somewhere lurking in the back. It's awesome, does very, very well. But much to the chagrin of our marketing team, we FP occasionally, and so we're not perfect by any stretch. So we internally want to understand how to get better. So that's understanding what features are potentially not working the way we think they are, what decision paths could be compromised or taken advantage of, and then finally, do we just have training samples in our data set that just aren't that good? So I wanted to take all of that and then roll it into a service where you submit a sample and then it spits back a score metric so we could understand kind of at a human readable level what was going on with our model. The prior art, like I said, there wasn't a whole bunch, but these 3 papers, I highly recommend checking it out if you're interested in this at all. I took elements from all 3. I'm not going to rattle them off because you can only say evasion so many times, but the bulk of it had to do with hardening tree-based models, so either using adversarial boosting or leave one out training. And then really the crux or foundation of TreeHuggr was born out of this paper by Yahoo Research, which did brute force feature tweaking to make recommendations on ads. So to help their customers who had crappy ads have less crappy ads. And they would do things like recommend words they should use or images or text length and things like that. So as far as designing TreeHuggr, I wanted to build on that research in particular and try to use the Yahoo algorithm as much as possible because it had already been written and I had recently become very, very busy. I also, instead of setting out to target gradient boosted trees, I went with random forest first. It's a little bit simpler problem since it's just a majority vote. which is just makes life a little bit easier. And yeah, and then finally, I wanted to really kind of not necessarily set out to harden models to no end and say that we now have a silver bullet and everything's protected, but just add to the explainability. So things like SHAP and Lime and some of these other cool resources that had come out that explain model feature importance, I wanted something that tackled it from the FP and adversarial side of the house. So with that, the architecture and the way it's laid out, the middle section, the pre-processing section, is really born out of the Yahoo research. So this idea of going through, extracting all positive paths from a model, and then performing this feature perturbation, that's all available open source through Yahoo. If you check out that paper, I think they link to it, their GitHub. And then on the right-hand side, the red boxes, that's the area where I kind of focus my time. Once you have those perturbed feature vectors, what all could you learn from it? What all could you do with that? So that's where adversarial generation, identifying common features or decision paths that were exploited or evaded, and finally this concept of a susceptibility score, which I'll dive into in a few slides. So to explain this without showing you a ton of math, I'll try to do an animated GIF through PowerPoint and kind of walk you through it. So at the top of the screen, you have a feature vector for a piece of malware. You know it's malware because there's a little red bug next to it. And then this is one tree within a random forest. So this lays out the features and kind of the conditions required to end up in one sort of leaf or terminal node. What we do is we highlight the features and walk the path, and then the path says at the end, this is malware, that's their vote. If other trees, the majority of trees call it malware, then it's malware. Majority rules. Very, very exciting. What TreeHuggr tries to do instead is it goes through and says, all right, show me every possible way this could be called a benign piece of software. So we kind of iterate through, we identify them all, and then we say these split points, these features are the ones that could be susceptible to tweaking or perturbation, and these are things we're going to explore. And then it goes through each one of these conditions, each one of these decision paths, and I'll just show one for brevity, but it says we'll start here at this main node, feature 0, and then we'll try to end up here, the little green box at the bottom right. And what we'll do is we'll say, okay, at feature 0, we need to be less than or equal to 0.9. And we look at our feature vector at 0.79, and we say, that's not going to work. We need to head down the right side, not the left side. So what do? We apply this feature transformation. And all this feature transformation is identifying the threshold. So in our case, it's 0.9, and then adding a global epsilon value. So this just gets you above or below the threshold as small as humanly possible. We do that. We get 1, we add it to the new feature vector, which is x hat, which is very formal. And then we move on to the next decision. Next decision, feature 2 needs to be greater than 0.8. Well, it already is. Again, we want to keep going down the false side, so we apply the same methodology. We identify the threshold, 0.8. This time we want to go below, so we subtract by 0.1. And we end up with 0.7. We do this over and over again until our label changes, and we're done. Now, I could just mic drop right here and say, like, yeah, I can defeat any tree-based classifier, but that isn't really the case at all, and that's not how random forests work. Any change that you make to this feature vector could actually have a catastrophic effect to the rest of the trees in the forest. So this sort of butterfly effect kind of cancels out how effective you could possibly be taking this approach. What you need instead, and kind of the satisfier that I require in order to make it to the next step, is that the tree, so the local instance or micro instance, needs to call this a benign sample, and the global or model itself needs to call this a benign sample. If both those pass, then it gets added to a queue, and then that goes into the adversarial generation component, which takes us to the experiment setup that I kind of did. Ember, I don't know if you guys have heard about it. It's only been mentioned 35 times. Hiram and Phil did excellent work to more or less replicate or create an adequate representation of the features that we use internally to Endgame. So I wanted to use that. That way I could talk about it here. And the interesting thing about it, at least from an adversarial standpoint, are the way the features are broken down. You have byte-level features, which are things that I would rather not muck with, because that's very, very difficult, versus PE header pieces of metadata, so strings, imports, exports, header information like timestamps. These things are a little bit easier to change within a file. They make them a more realistic attack vector. So the models that I built were random forest, scikit-learn, very base, range of trees, range of samples, and capped max depth, so my laptop didn't catch on fire, and created a model that was not suitable for any sort of actual work. Detection rate, 1% FPR was about 95%, but it got the job done because I wanted to detail offense, defense, and interpretability use cases. So this moves us into the post-processing phase, which we'll kind of walk through right now. The first experiment that I was really doing was generation of adversarial examples. The threat model behind this isn't particularly sexy. White box attack, you need to know the features, the model, like literally everything. So this is more for internal use only. But I wanted to take true positives and move them to false negatives, so evasion attack. And we were moderately successful. We were able to generate a bunch of solid adversarial examples. The evasion rate actually decreased quite a bit the more complex the model got, which isn't overly surprising because that's more decisions and branches that you end up rolling into. So once I had that, I needed to understand why these things actually worked, which moves us into the interpretability use case. What I wanted to do was really highlight the where in all of this, like where within the model are we susceptible, and see if certain features or certain paths were promoted more often than not for evasion. And the results were pretty illuminating. For the perturbation side of the feature set, it was a lot of header section, general file information, things like that, which was great. The other good thing is that they didn't line up exactly with just hitting .feature importance on scikit-learn, which meant that I at least did something different, which is always nice. Now from decision paths, that's where it got interesting, at least for me. Decision paths, I think there were like 2,000 within the model, but some of them were being recommended 10-15% of the time, and this is actually the top one for one of the crappier models, but you can start to see histogram features were more or less unchanged, but the header and general file information, which were highlighted under common feature recommendations, were highlighted here. So the next step on the interpretability side was developing this concept of a susceptibility score. Something that told you, hey, if it's close to 1, this thing is really bad. Could confound a model, could potentially be tweaked or perturbed in a way that completely evades everything. So all that would do would take your target sample, generate as many adversarial examples as possible for that sample, and then take kind of the max or the highest performing one. So the one that actually minimizes the amount of changes that are required. So at the individual feature level and then across features. So we just wanted to minimize that. So things like this sample only required you to add a single import to the import table, or just required like a single string to be manipulated. Those were incredibly evasive examples. And the distribution of that was kind of interesting. We didn't have too many generated that were like 6 or 7 features that required perturbation. Most of them were like 1 or 2. Granted, this was on a model that wasn't state-of-the-art by any stretch, but interesting nonetheless. And then once I had that score laid down and the adversarial examples kind of mapped out, I moved into defense. Like, could we actually harden these models? And this was a real mixed bag. Kind of a bummer, but these things happen. So what I tried to do was create adversarial examples of the training data and then do adversarial boosting. So kind of add those to the data set. And I had a small little algorithm that gave me a budget, a perturbation budget, because I didn't want samples that were like crazy 200-300 features requiring to be changed. I wanted it nice and tight, 3, 4, 5 features total. What that did was that it increased the malicious training set by like 3x, which was suboptimal, as you can see on the right. The overall detection rate dropped considerably, and I chalk that up as a pretty big red fail. But then I kind of moved forward and started thinking, I'm like, well, maybe this new model that's less good at kind of detecting, maybe it's still hardened against evasion attacks. And for that, it actually showed some promise. Evasion rates dropped considerably, which was good, but it came at the cost of overall detection rate. And that kind of leads to a lot of the research that you see, which is you can either have a model that's hardened and secure, or you can have a model that's really good at classifying things. There's kind of no free lunch there. The next thing I wanted to do was leverage that susceptibility score and rank so we could identify the most dangerous samples within our training set, and was able to do that. Very, very simple. And then I wanted to remove those from the training data to see if our model got a little bit better there. And I was pleasantly surprised that it didn't kill detection performance. It bumped it up a little bit, and it's an experiment that kind of needs more work. I just did leave one out, retraining there, which was moderately effective, but not ideal. But I called it a success anyway, and maybe that was based off of the 2 less than spectacular experiments that came before. So yeah, that was kind of TreeHuggr in a nutshell. There were challenges abound, particularly from trying to do this on a laptop. Random forests have the potential to be huge. You are brute forcing every possible permutation, so number of trees by positive paths, by total features. This can get pretty nuts pretty quickly. And then the one random aside that I had was that the features themselves kind of needed to be scaled, which is not something that needs to happen in tree-based classifiers in production. But when you're applying this approach, in order to have a single epsilon value go across, you can't have certain features that are like range 1 from 10,000, and then another one that's like -1 to +1, because then your epsilon value does not match that. It needs to be standardized. So for next steps, we are going to flesh this out a little bit more and turn it into a service. So every sample that kind of comes through our pipeline gets these susceptibility scores, and we start to understand how our model votes against it, which will require migration to gradient boosted decision tree, because that's what our model is in. And then finally, just kind of go back to those defensive experiments with the help of other folks within Endgame data science, and see if we can flesh those out and turn it into a paper, either a white paper, something on archive. So, in conclusion, I hope that TreeHuggr would bring about a little bit more novelty than I think it personally did. I think there's potential there. It just hasn't been maximized yet. Granted, this is not a realistic attack by any stretch of the imagination, but it's still useful for kind of poking and prodding a model to understand where its weak points or blind spots are. And then finally, it brings me into a point that I was talking to Fernando about actually at lunch, which is this idea of how do we, as data scientists, help red teams and blue teams account for the fact that the security stacks they are attacking and defending have more and more machine learning in it. This is something that, with the folks in the crowd, I would love to have a conversation with when I wrap up, because it does seem highly probable at some point data scientists are going to have to play a part in both attacking and defending these to make consumers of this technology feel a little bit more comfortable about the money they're spending. So with that, I am wrapped up. Any questions?
Perfectly on time, thank you. Do I have this thing on? Oh, okay. So I guess we start with that first question then. So red and blue teams, should they be included in adversarial ML yet? And how are they likely to do it?
Yeah, so probably not yet. As cool as it would be, a lot of the attacks still aren't very practical. But I think there are several of us here who have models that sit on VirusTotal, and that's just basically a free service that allows would-be attackers to kind of poke and prod your model, particularly if your model produces any sort of score. Like if you report back a score, then that's a nice feedback mechanism for anybody who has an inkling of like machine learning prowess that they could then in turn build samples that kind of manipulate up and down the spectrum.
All right, let's see if the mic works. It's been kind of on and off today. One kind of clarification and then a question building on that. When you were looking at the procedure for perturbing features, I was a little confused about what epsilon was doing, because it looked like it was giving you a padding above the threshold specified in the model as opposed to being the amount by which the underlying feature value changed. So I just wanted to confirm that that was the right understanding, because my baseline would be like, oh, epsilon represents how far we're moving the feature from its baseline value. So if you could clarify that, and then maybe just an addendum on top of that is, do you think your susceptibility score could be used to, for example, compare how susceptible like a neural network model and a tree model are on the same data set? Or is it too specific to tree models?
Yeah, so regarding your first question, the epsilon value is inherently tied to push you above or below the threshold. And then the idea is that the susceptibility score would capture how much movement or the magnitude of that change from the original feature vector. So yeah. Great question. And then the second one, as far as susceptibility score being used as like a comparator to neural networks, that's interesting. It's something I haven't thought about too much. In fact, the next thing I wanted to tackle as far as scoring mechanisms is susceptibility score is tied to a model and a sample. It would be interesting to provide a susceptibility score for a model writ large, right? So as Phil or somebody on my team produces a new model, they run it against this and it's like, oh, your susceptibility score went up from last month. Why? What did that data look like coming in the training pipe that changed that? I'm not 100% sure how that would be tackled. But yeah, that's kind of where I'm at right now. Thank you.
So, yeah, so you had mentioned that the fact that really the only ordinal values matter when you're fitting a random forest, right? The only thing it's looking at is what's bigger or what's smaller than your cutoff point. Do you think, and then also that you had to rescale all of your inputs to make this sort of epsilon perturbation actually work. So it strikes me that that's maybe an interesting, there might be a way to combine those two facts to maybe be another way of hardening random forests, at least, against this, maybe by randomly rescaling your inputs and then selecting cutoffs that maybe aren't exactly like one point. And as someone who's thought about this a lot more than I have, I was wondering what you thought about that.
Yeah, that's definitely an interesting idea. Certainly something that I was considering was just when I realized that you had to do the feature scaling to begin with, I'm like, well, that doesn't necessarily make your recommendations, the features that are being tweaked, understandable, right? So there was kind of like a little reverse engineering that had to occur where when the recommendation came out that it's like strings needs, this string value at this feature index needs to be adjusted by Y, like how much is that really? So that reverse engineering and kind of undoing the scaling is something that I had been considering, but I didn't really think about it as another avenue for hardening the model. Yeah. So yeah, definitely good call there, I think.
So I think building on that question, or perhaps a related question, the thought that just passed by my mind was the intuition of minimizing this epsilon sort of makes sense intuitively if you think that the features are all these sort of continuous things that the most similar thing will be not too far along one dimension. But have you considered, or maybe you've already thought about this, a different measure where you're not minimizing sort of the distance along each one of these dimensions, but the distance from like an actual observation in your training data set? The idea being that maybe if you tweak this one feature just a little bit, that actually makes it like something very unusual to observe, but when you're trying to hide, you actually want to look like something that was in the training.
Yeah, so Hiram, Phil, and I actually worked on something similar a few months ago where we were tackling that exact problem, where it was just like, if you make a recommendation that a string needs to be changed, what does that actually do? Is there some sort of systemic effect if you add the word the randomly in your list of strings, like that could in fact alter byte histogram, byte entropy, things like that. So yeah, I think long term, in order for this to be useful in a more operational setting, things like that have to be considered. Otherwise, you find yourself in a situation where you're making recommendations that just aren't feasible in a real world setting. And really, again, your point highlights how domain specific and how much intimate knowledge you need to have about both models and features for this to work, which was one of the main reasons why even supplying source code for something like this was nonsensical. But yeah, I'd be more than happy to talk about that more offline.
So, so there, like in crypto, there's this notion of Kirchhoff's principle, which is basically assume like the methods, the algorithms are public, the key is the only thing that's private, and then there's like Shannon's maxim, which assumes like the enemy has the design of the system. And so my question in terms of adversarial machine learning is that, do you think that's a very strong assumption to that, or you think that would be a principle that should be adhered to in terms of the machine learning, is assume that how your algorithm works, that is going to be public, and basically you work on that assumption instead of obscurity by security, or should that be relaxed some? So. Yeah,
that's a great question, and certainly one that I think any company that puts something out there publicly available has, at a minimum, has to consider, and maybe even more so for security companies. I think with the rise of next-gen AV and machine learning-based malware classifiers, and VirusTotal, that represents a good opportunity for would-be attackers to better understand what security companies are focusing in on. So yeah, good question, and good luck.
Yes, it was amusing when the next speaker asked the question
Yeah,
to the last speaker.